Welcome to lesson number 3 of this Technician License course. In this lesson we will be talking about the fundamentals of radio and electronics, including antennas and feed lines. Here is a diagram of a dipole antenna. Notice that it is a horizontal antenna made of 2 radiators, an insulator in the middle, and a feed line. Dipole antennas can be strung horizontally, vertically, sloped, or installed as an inverted V. Here is an example of a couple of commercially made dipole antennas. They are not hard to design or to build. Looking into the end of a dipole antenna, the signal in free space goes in all directions equally. Looking down on the dipole antenna from above, the signal is strongest broadside to the antenna. A dipole antenna can be made to work on several bands by using tuned circuits between each antenna section. These tuned circuits can be made from coils of wire or coils of coax, which are tuned circuits using the impedance, the inductance, the capacitance, and the resistance of the coax. Vertical antennas are usually 1/4 wavelength tall and need radials to make up the other 1/4 wavelength. These are called ground plane antennas. Vertical antennas can also be made multiband by using tuned circuits between the resonant sections. Verticals have a lobed elevation pattern, but are omnidirectional when viewed from above. A Yagi antenna is like a dipole with more elements in front and behind the radiator. Yagi antennas have gain in the forward direction. The more elements, the more gain, and the narrower the pattern. Yagi antennas have at least 2 elements, can be one band or multiband, and have gain over a dipole in a specific direction. Notice that Yagi antennas have a lobed pattern in both elevation and azimuth. The main lobe is what produces the gain. Multiband antennas can be made from several dipoles or inverted V's with a common feed point. The electrons figure out which set of dipole wires to use. This antenna is very simple to design and to build. Your antenna is the single most important part of your ham station because it launches your signal. Your feed line connects the ham rig to your antenna. Test equipment and antenna and feed line matching equipment help you monitor the performance of your station and the performance of your antenna system. The driven element of your antenna is generally the element that your feed line is connected to and is where your transmitted energy enters the antenna system. The antenna may be vertically, horizontally, or circularly polarized. Some antennas are omnidirectional, meaning that they radiate equally well in all directions. Some antennas, such as beams, focus radiation in a particular direction. If an antenna has gain, that means that there is an increase in power in a particular direction and a decrease in power in other directions. Here is an example of an antenna radiation pattern looking down from above. The further the line is away from the center of the graph, the stronger the signal at that point. The chart on the right shows the radiation pattern looking from the side. This antenna has a nice low takeoff angle, but it is also a bit of what we call a cloud warmer. As you may recall from last time, antennas act like a capacitor, an inductor, and a resistor. The response to alternating current AC is called impedance. Antennas have a characteristic impedance. A common value is 50 ohms, which depends on lots of different factors. The impedance of the transmitter, feed line, and antenna need to match. If they don't match, you don't get as much power output as you might otherwise. The most popular type of feed line is coaxial cable, called coax. There is also open wire ladder line. Each has a characteristic impedance and is used for certain applications. Here is a drawing of coaxial cable. Notice the center conductor, the dielectric, the braid, and the outer jacket. Coax is the most popular type of feed line because it is fairly easy to use, and most of it has a 50 ohm impedance, even though there is some signal loss. Open wire ladder line is not as common these days because it is more difficult to use and because you generally need an antenna tuner to get a good match. It does have very low loss. Impedance matching to your antenna feed line system is important. An SWR meter and an antenna tuner are a couple of key test equipment items for your station. If the transmitter, feed line, and antenna impedances are not perfectly matched, some RF energy will be reflected back into the transmitter. This reflected energy is generally converted into heat or unwanted radio energy. The ratio of energy going out to energy being reflected is called standing wave ratio, SWR. The SWR meter is generally inserted between the transmitter and the feed line to measure how much energy is being reflected back into the transmitter. You generally adjust the antenna to minimize SWR. A 1-to-1 SWR is perfect and means that no energy is being reflected back into the transmitter. At 2-to-1, most modern radios start lowering their output power automatically. At 3-to-1, you generally need to do something to reduce SWR. Antenna tuners are impedance transformers that can help match the feed line antenna system impedance to that of the transmitter. They cannot help make a bad antenna into a good antenna, however. To use an antenna tuner, you adjust the antenna tuner settings to minimize the SWR. What type of antenna is a simple dipole mounted so the elements are parallel to the Earth's surface? The answer is B, a horizontal antenna. How would you change a dipole antenna to make it resonant on a higher frequency? C, shorten it. What does an antenna tuner do? The answer is A. It matches the antenna system impedance to the transceiver's output impedance. What generally happens as the frequency of a signal passing through a coaxial cable is increased? D. The loss increases. What might cause erratic changes in SWR readings? The answer is B, a loose connection in your antenna or feed line. Which of the following is true of PL259 type coax connectors? C, they are commonly used at HF frequencies.